All right, so we're going to discuss in this video a very important and fun concept known as the concept of electrostatic shielding. So this is the concept that is at work in when we talk about Faraday cages. So we have here a metal enclosure that the shape of the metal enclosure is irrelevant. The spheres are nice and symmetric, so that's why we consider a spherical metal conducting shell. And outside that shell, we have a plus q point charge. So it doesn't have to be a point charge, it can be anything. So let's consider this to be your point test charge that you carry with you all the time in your pocket. And we know from our very basic lessons of electrostatics, whenever you have a positive point charge, you have electric fields coming out of it. It's a source of electric field. So therefore, of course, you'd expect that electric field to go everywhere in space around it. Definitely. So it's going to penetrate the conductor in all possible directions, wherever it sees the conductor, because there is no reason to just for it to just vanish in thin air. So it's going through everywhere around it. It's basically the source of the electric field in space everywhere around itself. So the conductor is kind of in the region of that electric field. So the question we ask is what is going on inside? Is the electric field inside the inside uh, that is getting inside really affecting anything in the conductor? But there's this important thing in electrostatics that we know from Gauss's law that the electric field is zero inside a conductor, any conductor, and that is defined as the electrostatic condition or the electrostatic equilibrium. So that means, what is an electric field? Well, electric field is anything that will enable charges to flow in it. So positive charge will flow in the direction of the electric field, while negative charge will flow opposite to it. Now we know metals that are conductors have many free electrons. Electrons are nothing but negative charges, and they're free to move about. In electrostatic condition as well, they're always moving about, but there's no net motion. So they're not moving about in a very regular manner. So if you go ahead and think about an electron, let's say anywhere in the conductor, then what would an electric field inside the conductor mean? Well, think about it while I erase this electric field, because I know now that the electric field inside the conductor must be zero, but I want to understand why that is. Well, what happens to those free moving electrons? Well, if you consider any electron in the conductor itself, we know that any electric field will want to move against it. All right. So if there were electric field, then the electrostatic condition would be violated. So the electrons would start moving. We don't want that. So out of nowhere, the electrons are not going to move out, and so the electric field inside the conductor must then be zero. So how is that becoming zero? That's the question. Well, the electric field outside is that of a point charge. So then all the electrons, they will move under the influence of electrostatic force. The positive charge will draw all of the electrons or many of the electrons as close to it as possible. The electrons cannot really escape the conductor, so they will collect to as close as possible to that negative to that positive point charge. So the nearer surface that is to the point charge plus q, the nearer conducting surface will become overall negative because of the presence of that positive charge. That means the electrons that have come here have left empty spaces behind, and those then become devoid of electrons or positive charges. So the far end of the conductor is positive, the near end of the conductor is negative. So that really creates its own electric field, right? That creates its own electric field, because I know whenever I have positive charge, that's the source. Whenever I have a negative charge around, that's a sink. So inside the conductor, there is its own electric field generated because of the motion of the electrons getting closer to that positive point charge outside. That electric field always, in electrostatic condition, always must exactly equal the electric field that is generated by any point charge or any charge that is outside, but the direction would be exactly opposite. So they will cancel out exactly, meaning that electric field equals zero. That condition is protected. The electrostatic condition is satisfied. All right. So then we can erase the electric field, because I know that this electric field is canceling out any kind of electric field buildup due to the positive charge outside. So basically, inside of the conductor, if I'm standing there, and if I'm touching the inner walls of the conductor, I am completely unknown. I'm completely oblivious to any charge or any electric field that may live outside of my enclosure. So this is the idea of a Faraday cage. So you can touch the insides of your metal Faraday cage during a thunderstorm. You don't feel anything. You're not going to get any shock. So basically, if a thunder strikes your metal enclosure, then what's going to happen? Well, the thunder is basically nothing but flow of charge, and without getting inside, because they are not allowed inside because of this opposite electric field, that electricity from the thunder will actually find another way to go to the ground and ground itself. So you're completely safe as long as you're inside a metal or a conducting enclosure. All right, so this is basically electrostatic shielding. You're completely shielded from any effect of electric field that may be living in outside of your enclosure. All right, so this is the idea behind Faraday cage. So what is a good example of a Faraday cage? Well, can be anything. Can be an aeroplane. Airplanes, when they're hit by lightning all the time, they don't get affected because the surface is made of metal, and you sitting inside the airplane has no way of knowing that whatever has happened outside. All right. So elevator is also a Faraday cage. So that's why it's hard to make calls inside elevators, because Faraday cages also block out electromagnetic radiation. All right. So the only way it works is that if it's made up of conducting material, and we know that metals are very conducting material. So this leads us into the idea of equipotential surfaces. We know metals are equipotential surfaces. What does that mean? That means everywhere on the metallic surface, the potential is the same. So if you have a point A and a point B, and you want to move a positive point charge, a test charge, from A to B, what is the force that you feel? Well, there is no electric field inside the conductor. So going from A to B means that you don't have an electric field in that region. And if you don't have an electric field in that region, what about the electrostatic force that you feel? Well, the electrostatic force is defined in terms of the electric field. We know that the force F, the electrostatic force, is the electric field is defined in terms of F over Q. Since the electric field is zero, but the charge is positive, so the force must be zero. So if the force is zero, then moving from A to B would mean that you don't do any work, because work is defined as force times the distance, right? So moving from A to B means that you don't do any work. And in terms of the potential, electric potential, what does that imply? Well, that implies you don't do any work per unit charge. So we know that electric potential energy is U. It is, when divided by whatever charge you're carrying, becomes the electric potential, capital V. And this means the potential from A moving to B, you are not going through any change in the potential because the electric field is zero. If the electric field is zero, you don't do any work to move from A to B. So since electric field is always zero inside conductors in electrostatic condition, inside a conductor, all potential values are the same. So moving from one point to another inside, you don't do any work at all. So whatever work you do is carrying that point charge to the surface of the conductor. When you enter inside, you don't have any work. You don't need to do any work inside to move about. All right. So the idea is that your electric field in this case must be perpendicular to the equipotential surface. So we know that is automatically true for a spherical conductor, because spherical conductor have radial electric fields. So if you have a radial electric field for a point charge and you draw equipotential surfaces around that point charge, you know what the shape is. Think about what the shape would be as I draw more electric field diagrams. So these are all electric field vectors. They're going everywhere. For now, I'm considering that electric fields are being penetrating the conductor. In this kind of a scenario, we can clearly see that the point of intersection of the electric field vector and the surface, they're not making 90-degree angles. The intersecting points are not at 90 degrees, clearly. But electric field must be perpendicular to any equipotential surface, and the metal shell is an equipotential surface. So therefore, for a common equipotential surface, how is the electric field going to change? So let's say this positive charge wants to have electric field everywhere around it, but the electric field around that point charge actually must bend, because it must maintain that wherever it touches the equipotential, or in other words, wherever it intersects the metal enclosure, then the electric field vector or the electric field line must be perpendicular to that surface. So the electric field vectors or electric field lines must themselves bend to accommodate that. And that must always be true because electric field must always be perpendicular to equipotential surfaces. So if you have a metal enclosure, this condition must be satisfied. The electric field must bend around it to accommodate the fact that electric field must be perpendicular to your equipotential surfaces. So what it would be the case if you were inside the Faraday cage, but now you were basically carrying a positive charge with you, positive point charge with you in your pocket? Well, if you're in the center, no problem at all. Well, the only condition the electric fields must satisfy is that they must be perpendicular to the equipotential, that is the metal surface. And everywhere you can see, if you draw these straight lines, you see that the electric field vectors make 90-degree angles with the surface of the conductor. So there's no problem at all if you're at the center. But what if you're off center? What if you're not exactly at the center? What's going to be the case then? That's something interesting to think about. Well, let's consider that you're here. With your point charge, you're basically here. Remember, the only thing that you need to accommodate is that electric field must be perpendicular to your metal surface, which is an equipotential. So here as well, inside, the electric fields will no longer be straight lines, but rather they must bend to accommodate that. So how would they bend? Well, very close to the charge, you will have stronger electric fields because more electrons will get to the places nearby because of that stronger pull. Away from that positive point charge, there will be less electrons. So the electric field must be strongest very near, in the near end towards to the charge, and kind of weaker on the farther away from it, right? So then you can, once you have drawn this charge distribution, you can now easily draw the electric field. The electric fields must bend. It must come out of the source and go into the sink. The electric fields must bend. Why? Because in this scenario, the electric field vectors will be perpendicular to the metal surface, and that must be true because you're in electrostatic condition. The equipotential surface must be perpendicular to your electric field lines. All right. So the next variation that you can think about, okay, let's move this charge around and let's all draw our electric field lines. So since the inside surface has become negatively charged because of the electrons being pulled close to the positive charge inside the cavity of the metal shell, the outside surface then becomes positive. The electrons have moved away from them. So what do the field look outside of the Faraday cage or outside of your enclosure? The electric field inside must be zero. Electric field inside the cavity is not zero because it's vacuum inside and you have a charge with you inside. But the electric field from the surface, what does that look like? Well, that is something that I leave you to think about. What would be the electric field that is outside? How would the electric field look that is outside of the outer shell?